Madam, 2 minutes, please.
Yeah, sure, sir. Yeah.
Thank you. Thank you.
Dr. Pallavi Madam, Dr. Emilette is our principal. Pallavi Madam.
Yeah, I think.
Very nice. Very nice to know, sir.
Namaste.
Namaste.
Yeah.
Sir, good morning, sir.
Morning, sir. Good
Morning,
morning. Good morning.
Good morning, sir.
Sir, very good morning, sir.
Yeah, good morning to everyone. Sorry for the delay. So we can start.
Yes, sir. Good morning, sir. We shall start, sir.
Yeah, good morning. Yeah, please.
Ashok, please.
Okay. Sana, madam, please.
Morning all. Happy Engineers Day to all the engineers gathered here. Seeking the divine blessings of His Holiness, Jagadguru Dr. Sri Shivaratri Rajendra Mahaswamiji and Jagadguru Sri Shivaratri Deshikendra Mahaswamiji, we have gathered virtually on this online platform to attend research talk on Knowledge Graphs, Fabric for Enterprise Data, organized by the Department of Information Science and Engineering on account of commemoration of 106th Jayanti celebration of Jagadguru Dr. Sri Shivaratri Rajendra Mahaswamiji. Now, I request our HOD, Dr. Rekha PM Madam, to welcome the gathering.
Thank you, Sahana ma'am. Good morning to each one of you present today. Happy Engineers Day to one and all. On behalf of JSS Academy of Technical Education Institution, I, Dr. Rekha PM, welcome our Honorable Joint Director, Dr. HR Mahadeva Swami, TED, JSS MVP. A warm welcome to our beloved Principal, Dr. Muthunjaya Vilate, for gracing this occasion. I heartily welcome to our Chief Guest Speaker of the Day, Dr. Rashmi Kamath. Ma'am, it's an honorable moment for our institution to have your prestigious presence in today's event. I welcome deans, heads of the department, faculty, research scholars, and students. A warm welcome to all who took out their valuable time and joined us today to be a part of this webinar. We are honored to have you all with us. Good morning once again. Welcome you all. Thank you.
Thank you, Madam. Now I request our Joint Director, Technical Education Division, Mysuru, Dr. H.R. Mahadeva Swami, sir, to address the gathering.
So very good morning to everyone. Welcome to
Morning,
this
sir. Morning.
talk on the data graph fabric. Then maybe for next 1 hour, there will be a good session on the subject chosen. Maybe today, maybe if you look at the scenario, maybe knowledge graph fabric for enterprise data. Maybe if you look at today, many of the things are happening. Maybe whether you take a social media or analytics or AI, are going in the direction of the data analysis or data analytics. So again, so remembering the Sutturum Parampare, offering my pranams to His Holiness Jagadguru Shri Shivaratri Deshikendra Mahaswamiji, and offering my pranams to His Holiness Shri Shivaratri Rajendra Mahaswamiji. And this particular 106th birthday is celebrated in this particular month. And in memory of that, we are conducting this program at JSCT Bangalore, and that too organized by Department of Information Science and Engineering of JSCT Bangalore. I think I congratulate and also appreciate the effort taken by all the organizers, maybe Dr. D.V. Ashoka, and then HOD and other faculty to arrange this particular lecture on the topic. Maybe just to add to a few points, which I don't want to take much time because the resource person will talk more on the subject. Maybe if you look at the today, as I mentioned, the data analytics and data analysis is becoming more and more in terms of the usage, because the large number of data is coming in. Then so maybe, for example, it could be a data fabrics or the use cases for a testing. It is not that easy. So when you want to go for that particular thing, maybe you require to be have a knowledge on the many other things. Maybe one of that could be like a graphs fabric for enterprise data. Maybe enterprise data is because very voluminous. It's not just simple data what you get. So it could be sales, it could be marketing, or it could be any maybe the manufacturing data. A lot of data will come enterprise data. So that is the one part. Second part could also be, for example, if it's a e-commerce company. The large data comes in. Basically, the data in terms of the emotional feeling of the user, emotional the status of the person. A lot of data will come. So in terms of e-commerce companies, they get from the consumers, from the customer, from the vendors. A lot of data will come. So now, using the data, how can we improve? That is basically what people are talking about in the data analytics. Maybe this session. This particular session on the topic, what is given as a knowledge, the knowledge data, knowledge graph fabric for enterprise data, definitely it will help to all our faculty, staff, and also the students, and also the other participants who are participating in this one. And I take this opportunity to thank the organizers for arranging this one, and also the resource person, Dr. Pallavi Karanth, who is a researcher at the Novartis Bangalore, accepted our invitation and giving this particular talk and letting us this particular topic. So I take this opportunity to thank again and wish this program a grand success. Thank you so much.
Thank you, sir.
Over to you, sir.
Thank you. Ashok.
Okay. Thank you, sir. So now
I request our Dean Research and Professor, Dr. D.V. Ashoka, sir, to introduce the speaker, Dr. Pallavi Karanth, madam.
Good morning. Happy Engineers Day to one and all, with the blessings of His Holiness Mahaswamiji. Now I am going to introduce the speaker of the today session, Dr. Pallavi Karanth. Pallavi is passionate in the areas of semantic modeling, of semantic data construction, and validation of knowledge graphs. She has more than 10 years of experience in various semantic web technologies such as RDF, WOOL, linked data knowledge graphs, along with analyzing semantics rich data to help in better recommendation and retrieval. She holds a doctoral degree in computer science and engineering from PS University, Bangalore. Her thesis titled Developing a Framework for Knowledge Analytics has been awarded as the best PhD thesis by Board of IT Education Standards for the year 2019. Congratulations, madam. She has served in various organizations such as Robert Bosch, Business and Engineering Services, Symphony Services, and PS University. She has worked earlier as a research assistant in World Bank funded Center for Excellence in Knowledge Analytics and Ontological Engineering. Her work in the research areas of knowledge management, analytics, and semantics have been published in many international journals and conferences. She is currently a volunteer at Knowledge Graph Conference KGC 2021. Apart from these, she has classical dancing and baking as her favorite pastime. Madam, this is your brief introduction. Lengthy 3-page introduction is there, but now there is no time. So I am very happy about your profile, madam. So welcome, madam. Please.
Thanks a lot, Ashok sir. Happy Engineers Day to one and all here. I thank JSSAT for this opportunity to have a discussion on knowledge graphs, fabric for enterprise data. So yeah, please feel free to interrupt me at any point of time, or we can as well have the questions towards the end. So let me start my presentation. Yeah, is my screen shared?
Yes, ma'am. Yes.
Yes, ma'am.
Okay. So yeah, we'll start off. So as we all know, the topic for today's presentation is knowledge graphs, fabric for enterprise data. So now let's see what is the agenda for us today. So we'll just see some interesting facts about data and then see what is a graph. And we'll also see informal to formal representations of knowledge. Knowledge can be represented in many ways. So we'll see which are all those representations and what is a knowledge graph and what isn't a knowledge graph, and why graphs for representation of data or knowledge, how is data modeled as a graph, exploiting data from knowledge graphs for a myriad of applications, and research directions which can motivate many of us to take up any research in this field. So now coming to some interesting facts about data. So in year 2020, each person created about 1.7 megabytes of data per second. Okay, and by 2022, it is estimated that 70% of the globe's GDP will have undergone digitization. Already we have seen, right, in post-COVID times, we all use digital methods of payment, and globe has undergone a lot of digitization, and we are about to increase the amount of digitization. And in 2021, 68% of Instagram users view photos from brands. And by 2025, 200 plus zettabytes of data will be in cloud storage. Already we have moved to cloud storage, and there will be much more data being processed in cloud. And in 2020, users sent around 500,000 tweets per day. So by the end of 2020, 44 zettabytes made up the entire digital universe. And maybe it's very surprising to imagine that around 306.4 billion emails are sent every single day, and 500 million tweets are made. So the rate at which data is getting digitized, data is getting produced, digital data is produced is at a very high rate. Say, as I told, every human being on the earth, if he or she produces 1.7 megabytes of data per second on an average, just imagine how much of data would we have. So extrapolating this figure, we have about 463 we would have 463 exabytes of data being generated each day by 2025. So that is a really huge amount, right? And now coming to how do we manage such huge amounts of data? So one thing is the data is not being generated in a single format, right? The structure could differ, and the nature or the context of the data differs. So we have huge diverse collections of data, and when it comes to linking such huge diverse collections of data, we should think of what data structure helps us basically to manage such huge structures of data. So in that sense, when we think, graph is one structure which is very, very flexible, and it helps us to manage large diverse collections of data. So I'll go into the basics. So what is a graph basically? So we would have a set of objects wherein at least some pairs of objects are in some sense related. So that is what we call as a graph. So we have nodes in the graph, and these nodes are connected by edges. Take an example of any statement. Say I would say JSS ATE Bengaluru is situated in Uttaralli Kengeri main road. So this statement, we have a subject, right? JSS ATE, located in is a predicate, and then we have the object Kengeri Uttaralli main road. So this statement can be represented in a graph using two nodes, and there is a connection between these two nodes. So that is located in as the connection between these two nodes. So in this sense, if you take any real world statement, it can be represented in a graph as a connection between any two nodes. And basically this structure, right? Subject, predicate, object, it is a triple structure. We call it as a triple structure. And therefore, it becomes very easy to model any real world data using a graph structure. And when we represent the data using a graph structure, the underlying graph structure itself helps represent the meaning of that data. The semantics of the data gets very well represented using a graph structure. And graph is one data structure which is very, very flexible enough. You need not think about the schema, high-level schema, or the actual structure of the data in the beginning itself. You can have it as ever evolving, and thus graph is the most ideal structure to represent huge, large collections of data, link the data, and then later analyze this huge collection of data. So we have various types of graphs, as we see here. We have directed, undirected, multi-graphs, weavers, hypergraphs. So I think we all know that directed graph has some kind of directionality for its edges, right? When there is, say, an edge from node A to node B, then it always means that the fact is true in this direction. But if we reverse the direction, the meaning of the edge will change. And when it comes to undirected graph, there is no directionality on the edges. And we have multi-graphs wherein there could be multiple edges between any two sources of nodes. And we have quivers, which are multi-digraphs. That is, there is direction on multi-graphs. And we have hypergraphs wherein an edge need not just connect any two nodes, but it could connect a set of nodes. Then we call it as a hypergraph. So this is a basic introduction of what is a graph. And now coming to the representation of knowledge. And this is a spectrum telling us how we can represent knowledge from most informal ways to the formal ways. So I think we are all familiar with Instagram, right? So in Instagram, we have free text tags, right? Say we can put a tag, I study at JSS ATE. I love computer science. So these kind of free text tags are the most informal methods of representing knowledge. And it is called folksonomy because we as folks kind of create these tags. So this is the most informal method of representing knowledge. Now coming to the next one, which is relatively formal to folksonomy, it is control list. That is, we will have a predefined set of terms. And it is basically a list of subject headings, or it could be a basically it will have a control list wherein there is control in the vocabulary. That is, some moderators are there to moderate the list and add or delete the concepts from the list. So now going forward, we have taxonomy. So what is a taxonomy? In taxonomy, we have relations between these lists of concepts. That is, the most preliminary relationship here is the hierarchical relationship. We have a parent-child relationship between the concepts in the list. That is when we call it as a taxonomy. So some of the relationships are like exact match, close match, broader term, narrower term. So such kind of relationships are present in a taxonomy. And we have simple knowledge organization system, SCORS, which is a standard for defining a taxonomy. And we have, for an example, medical subject headings. MESH is a standard taxonomy available in medical field. Now moving forward to ontology. So this is much more formal when we compare to taxonomy. So what does an ontology consist of? So ontology basically describes any domain and it represents the knowledge of that domain in a more formal sense. So we have classes and we have individuals or instances or the members of these classes. So this is very similar to object-oriented programming. So we have classes, we have instances, and how are these related? There could be taxonomical relationships, that is the parent-child relationships between the nodes in an ontological graph, and there could be much more than the taxonomical relationships. We can have non-hierarchical relationships between the members of such an ontology. So here we would get to express more semantics. So if you see, we can have different kinds of relationships in a graph, right? Consider Facebook graph, for example. So it is a social network. So a person A can be related to a person B using a friendship relation, or he can be related using a neighborhood relation, or he can be related using a business relation. So there are different kinds of relationships, and these relationships themselves can be related. So these relationships could be hierarchical in nature, or these relationships could be non-hierarchical in nature. So if you take the example of relationships like familial relationships, cousin, mother-in-law, brother-in-law, sister-in-law, and uncle, aunt. So there could be some kind of hierarchy between the relationships. There could not be any hierarchy between the relationships. So we could have relationships of two kinds, hierarchical or non-hierarchical relationships. So in this way, we would be able to express more semantics, more meaning to the data when we represent the data using an ontology. So basically, ontology is always restricted to a particular domain. And depending on the end application, we kind of design an ontology. And now moving forward to knowledge graph. So what is knowledge graph? It is much more formal compared to an ontology. It could have multiple ontologies coming together to form a knowledge graph. And as we know, when it comes to an enterprise, there could be large, diverse collections of data. And this data is, they could be different in terms of their own nature, context, or structure. So how do we model such data? So we use a knowledge graph to model enterprise data. So knowledge graph becomes like a fabric for enterprise data. And when we link heterogeneous data sources using multiple ontologies, it leads to further capabilities on this kind of data. Like we would be able to analyze such data as semantics is present. We would be able to infer on such data. By inference, I would mean that we gain additional knowledge by using a reasoner to infer additional knowledge on the data. So this is how we have classified the different representations of knowledge, right from taxonomy all the way to knowledge graph. And now moving on to knowledge graph. What exactly is a knowledge graph? So as I told, we have large voluminous collections of data. They're very different in their structure or nature or context. So taking into account all of them, how do we integrate such different data collections? So we integrate them and we try to manage such data. We extract some value out of such data using knowledge graphs. Knowledge graphs are they are ever evolving. They change over a period of time, and they represent the knowledge within a domain or a community. And when it comes to the schema, right, as I told, graph itself is very flexible in its schema. Like when you compare it to a relational database, wherein the schema is kind of well defined in the beginning itself, the graph has a ever evolving schema. The schema could keep changing, and normally the designers do not fix the schema in the beginning itself. And that way, it is very beneficial to model any data as a graph. And when it comes to knowledge graphs, how are they built? They are built on 3 different dimensions. So one is the schema, the high level structure. So it is like we decide what is required in order to give the meaning of all of the data. So that much is present in the initial schema or the high level structure of a knowledge graph. And then we have identity. How do we map the entities or the nodes in the graph to real world entities. That is when the data would make sense, right? When we map them to real world entities. I think there are a few examples in the future slides which will give us better clarity. And next, coming to the context. So a certain set of facts can be held true in a certain setting, right? There is a context, there is a scope of truth for a set of facts. So that is the context in a knowledge graph. And knowledge graphs are highly diverse in their structure and granularity. It could be a very detailed knowledge graph, or it could be at a very coarse level. So in that way, they differ in their structure or granularity. And we have two types of knowledge graphs. We have open knowledge graphs and enterprise knowledge graphs. So I think we are all familiar with open data sets, right? It is something similar to open data sets. So open knowledge graphs are those which are designed and made accessible for public good. The content is shared online and anybody can access them. So for example, we have DBpedia, which is the knowledge graph for the data which is there in Wikipedia. And we have Freebase, we have Yago, all such are open knowledge graphs wherein anybody can access and make use of it. And on the other hand, we have enterprise knowledge graphs. So enterprise knowledge graphs are very internal to any enterprise, and they consist of enterprise data within a particular domain or a community. And enterprise knowledge graphs, now you can take any company for that matter. Each company has its own knowledge graph to represent and manage data. So take, for example, Amazon. All of the Amazon's products are being represented in Amazon's knowledge graph. And similarly, Google has knowledge graph. By the way, the term knowledge graph was coined in the year 2012 by Google. So Google used this concept called knowledge graph in order to enrich its search results. I think those who have browsed or searched way back in 2004 or 2000, maybe in the last decade, you would find a lot of difference in the search results which are coming now to those days results. So these, the basic difference is Google has used knowledge graph to connect and link various sources of data, and basically it enriches its search results using semantically structured summaries. So that way, every enterprise for that matter has its own knowledge graph for internal usage, and it is not available for public good. So these are the two types of knowledge graphs. And now coming to knowledge graph Honeycomb. So this is taken from Ontotext. Ontotext is an enterprise which has GraphDB as one of the graph databases. So now coming to some concepts which are related to knowledge graph here. So knowledge graph is something which is very rich. It has rich data in context. That is, we have semantics backing up the data. And then we have explicit knowledge, which could be in terms of ontologies, taxonomies. There could be additional rules specifying the constraints between the different nodes and edges in the graph. And using such explicit knowledge in a knowledge graph, we can derive insights to the, from the data. That is, we can have explainable predictions and inferences. So we have semantic search and recommendation, which are some of the top applications for knowledge graphs. And we can also have machine learning models, which basically help us to classify the nodes or the edges. So basically, when we are constructing a knowledge graph, if we are not doing it manually, and if we have some kind of an automation to construct a knowledge graph out of, say, unstructured text, then we can use machine learning models to classify what is a node, what is an edge, right? All this can happen automatically using machine learning models. And what kind of content can go into a knowledge graph? It could be text, unstructured information. It could be images. It could be very well structured information. So all of these can make up a knowledge graph. And we have semantic metadata. So I think we all know metadata is data about data. So there are a lot of metadata standards, and Dublin Core is one of these metadata standards. And metadata can help us enrich the data further. And basically, data is the underlying constituent of a knowledge graph. So we can continuously link data, normalize data And all of these can be done with the help of business analysts, subject matter experts, data scientists, business users. And then we get a knowledge graph, which can be used for many applications. And now let's go into an example. So let's see what isn't a knowledge graph. So whenever we learn something, it also becomes important to know what something isn't, right? That is when our knowledge kind of becomes fairly complete. So let's see what is a plain graph. We have shoe brands here, which are having different properties. Like Ronverse is a brand, and Bike is also a shoe brand. And Ronverse is of color indigo, whereas Bike is of color bright crimson. And Ronverse is a sneakers type of shoe, and Bike is a running shoe. So we have a lot of entities here which are connected, and that is what makes a graph. So as I told, graph has many sets of objects, wherein some pairs of objects are in some sense related, right? So if we see here, Ronverse is related to color indigo and Bike is related to color crimson. So such connection between objects using the relations which are depicted by edges here makes up a graph. So what is the difference between this graph and a knowledge graph? So if you look at the second figure here, so what is the difference? So we have Ronverse, we have Bike, right? And both of them are brands of shoes. And we have two shoes, S1, two pairs of shoes rather, S1 and S2, and each is of a different brand. And each is a different style of shoe being used by a celebrity. And we have sneakers and running shoes, both are of type sports shoes, right? And sports shoes is of type shoes, and even boots or high boots is of type shoes. So we have some kind of a hierarchy here, right? If you see, so high boots is also a boots, high boots is shoes, and running shoes is also a shoes, which is a sports shoes in particular. So such kind of a hierarchical relationship is present here, and this is depicted in a shoe ontology. And then we have the colors, right? So we have indigo, bright crimson. So all of these are, indigo has a broader color blue. It has a parent color blue, whereas bright crimson has a parent color orange. And blue is some kind of a cold color, whereas orange is a warm color. And both of them are finally colors. So we have this classification of colors in a color ontology. We have a shoe ontology. And then we are specifying Ronverse and Bike as different brands. So if you see, brand is not a hierarchical relationship, right? It is a non-hierarchical relationship. So when we have a knowledge graph, we can have multiple ontologies. There is a context to it. So we are discussing shoes here, and we are discussing different types of shoes, the different brands, and how they have different colors. So there is a context here, and there are identities to real world entities. So S1 is a shoes owned by a celebrity, and S2 is another pair of shoes owned by a celebrity. So basically we have mapping to the real world entities. So we have identity, we have context, and we have some kind of structure to this data. And therefore this makes up a knowledge graph, which is in a way different from the plain graph what we have on the left hand side. And what happens when we do some kind of an inference on the knowledge graphs? When we do inference, right, like we add multiple edges based on the inference. That is, we are adding some kind of an additional knowledge to the graph. So if we see here, in this graph, it is not known that high boots is also a shoe, or rather running shoe is also a shoe, and indigo is a color. So that kind of an inference is made by using some kinds of reasoners. So when we use such inference, we get this additional dotted edges, right? So if we see high boots is a shoe and indigo is a color, so such kind of inferences are made by using reasoners, which adds additional implied knowledge. It would be there implicitly, but we make such knowledge explicit by using inferences. So this is one example to see what is a graph and what is a knowledge graph and how it differs from a regular graph, and what happens when we infer on a knowledge graph to add additional knowledge. And now going into why do we use a graph for representing data or knowledge? I think we started off there, right? Like data is huge. We have diverse, heterogeneous collections of data. So data is not uniform. It differs in its structure, and having such diverse collections of data, it becomes very simpler to integrate such data using graph models. And every day, the data keeps changing in its structure. There could be differences in the way we model data. And when it comes to a relational database setting, we are very much not so flexible in that sense that when we design tables, when we design attributes, it becomes difficult when we are adding more tables or when the data structure is itself changing. So to accommodate such changing requirements, graph model is the best way to model or represent data. And as I showed in the previous slide, we did some kind of an inference on the data, right? It becomes easier to infer and add additional knowledge to the graph data. And when we say it is a more intuitive representation, we can query these graphs to get the answers for our questions, right? So when we have any question, say which node is connected to some other node, we are not just talking about the direct relationships which are connecting any two nodes. It could be indirect relationships through paths. So by path, we mean a series of edges, right? And many querying languages allow us to query for the paths in the graph, and this helps us to find the indirect relationships between different nodes. So that way it is more intuitive representation. So as we have all of these strong reasons supporting us to accommodate different changing requirements, to link and integrate various diverse collections of data and add additional knowledge on the graph, it becomes very easy to use graph as a knowledge representation model. And now, how is data modeled as a graph? So the how part of it, we have two widely known graph models. One is a property graph model and another is a semantic graph model. So as I told, any statement can be represented as a subject, predicate, and object. And this is what we call as a triple structure. So when we say subject, predicate, and object, in that statement, when we identify the nouns in the statement, they become the nodes or the vertices in the graph. And the verbs or the actions within the statement becomes the relationships or the edges in the graph. So this is how we can basically design a graph and model data in the graph structure. So now let's take one more example, which could be very close to all of us. So we have universities, and there could be different universities. For example, Stanford, MIT are universities, and Peter, Professor David, Ben, Williams are all persons, or rather people, and Stanford CS, Stanford ENG, MIT CS are different departments, and there are different relationships like member of, advisor, undergrad from, and type, and sub-organization of. So if we look into these kind of relationships, we have type, sub-organization of, all of these representing parent-child relationships, and therefore they are hierarchical relationships. And there are other non-hierarchical relationships like advisor, member of, undergrad from, grad from. So in this way, we can model data as a collection of nodes and edges, right? And there could be some kind of a constraint or a rule present on the edge as well. So if we go into ontology, right, this allows us to constrain the relationship which is present between any two nodes. Say, I can say that Stanford has to be of type university, or rather Peter has to be a person and it cannot be an animal. So some kind of a constraint being put on the edge can be represented very well using an ontology. And now coming to the two different kinds of how we model a knowledge graph. It could be a labeled property graph. So this is one kind wherein both the nodes and edges have some kind of an identifier. They have unique identity, and every node or edge can have attributes. So how do we represent these attributes? It can be represented using key value pairs. And basically these labeled property graphs, they do not have any standard. It is not defined by any standard, and the semantics cannot be easily represented using, it is not explicitly represented using labeled property graphs. And we have different query languages which are specific to each implementation of labeled property graphs. So we have Neo4j graph database, which has its own query language Cypher. And similarly, Tiger Graph has Graph SQL, and Apache Tinkerpop has Gremlin as its query language. So basically, there is no standard here when we are representing the data using labeled property graphs. And now coming to the semantic graphs, they are basically RDF and OWL based. So by RDF, I mean resource description framework. So this allows us to represent any resource, anything in the world using a language called RDF. And OWL is a web ontology language, which can be used to model the knowledge in any specific domain using a lot of constraints, and it is basically more formal representation of knowledge. So as I said earlier, we have object-oriented programming, right? And wherein we understand what is a class, what is an instance. So the very same meaning is also here in terms of what is a node. A node could be a class or an instance of a class. So by class, we kind of group together certain common characteristics and call it as a class. Say in animal kingdom, I have reptiles as a class, I have mammals as a class, I have birds as a class, like that. And we have edges. They could, as I told, they could be taxonomical or non-taxonomical. These edges represent the properties of those classes or the instances. And basically, this is standards-based representation. So World Wide Web Consortium, W3C, has its own standard to represent semantics within the graph, and they are RDF and OWL. And here also, every node or edge has some kind of an identity, which is represented using IRI or URI. And as we know, graph enables us easy integration from multiple sources, and it is easily flexible for any kind of extension. So with changing requirements, we would be able to accommodate all such changes using this graph model. Now let's see one example wherein the same data is being represented using a labeled property graph and an RDF graph. So if you see here, what is the data that we are trying to represent? The statement is Bob manages Andy. So Bob is the subject, manages is the predicate, and Andy is the object. So this is being represented using a labeled property graph like this, wherein every node has a name and a title. So Bob is a manager and Andy is a developer. And manages is a kind of an edge that also has the property from when that Bob manages Andy, the date from when Bob manages Andy. So this is represented using labeled property graph using key value pairs of the attributes for both the nodes and edges. And if you look at the same data, how it is represented in RDF graph, so there is some kind of a schema here. So when we say Bob, Bob is of type manager. And when we say Andy, Andy is of type developer. And when we say manages, manages has an attribute from when, the date. Okay. So basically RDF graph is somewhat more dense when compared to labeled property graphs. So this is how we represent the same data using labeled property graph and RDF graph. Both are right and in their own sense. And we will see like what is the advantage of representing the data using semantic graphs. So semantic graphs are very rich in the sense that we actually capture the schema in the graph. That is, we are also capturing the type, right, as a particular node in the graph. So when we say Andy is a developer, the type developer or the manager class is also represented as a node. The schema becomes very much present in within the graph itself. And we have different validation mechanisms to kind of verify that whatever we have stated in the knowledge graph is correct or complete. So we have Shackle as a standard, shapes constraint language in order to validate such graphs, and that helps maintain data integrity. And all kind of rich rules can be well represented using semantic graphs. As I told, we can constrain the relationships. We can say a particular object belongs to a particular class, or we can say there is a minimum cardinality for a particular edge. Say when I say parent, a parent should have at least one child. So such kind of rich rules or constraints can be brought into the graph. And as we saw, inference adds additional knowledge to the graph, and there are reasoners which support inference on these semantic graphs. And we have globally unique identifiers for every node and edge, and these can be resolved when we are trying to link multiple data sources. So how do we resolve these identifiers? So that can be done very well using semantic graphs. And basically they are more evolvable, and they are best solutions for changing data requirements. And we also saw in the example, semantic graphs are much more denser when compared to property graphs. Now coming to the key aspects while designing a knowledge graph. So schema, what do we mean by schema? Some kind of a high level structure as to how a graph should be. So we have three different types of schemata. One is semantic schema, validating schema, and next is emergent schema. So what is semantic schema? Semantic schema states that open word, it follows open word assumption basically. So what is this open word assumption? So if we say we have a set of facts like JSSETE is a very premier engineering college in Bengaluru, and then we have JSSETE has different branches of engineering like mechanical, electrical, computer science, information science, and it also offers degrees in engineering, MBA, right? These are a set of facts given. But it is not, I mean, here we do not mention that JSSETE is in southern part of Bengaluru. Does it mean that the statement is false? When we have mentioned these set of facts, does it mean that the statement is completely false? That it is not in South Bengaluru? No, right? It just means that the data is absent here. So this is called as open word assumption. When we have a set of facts, say ABC, the fact D, about the fact D, we do not know the source of truth. We do not know whether it is true or false. So we just consider that the statement is absent in this set of facts. So that is open word assumption. Whereas opposite to it is the closed word assumption, wherein when a fact is not present, it is very imperative to think that the fact is false, right? It does not hold good or hold true. So in case of semantic schema, we usually assume open word assumption, wherein we think that the knowledge here does not consist of that additional fact, and therefore we cannot comment on whether it is true or false. And then we have validating schema. So as we told, like we have semantic schema to help us infer additional knowledge. And when it comes to validating schema, it helps us to validate the existing set of facts. Whatever is known is complete, right? And then we have emergent schema. So when it comes to emergent schema, we kind of take we partition the graph and take a subset of the graph, whereas we maintain the structural properties of the graph. So when we take the subset, the structural properties of the graph remain true. And next, coming to identity, any resource or any node in the graph is uniquely identifiable. So we can use a URI to identify any resource. That is universal resource identifier, right? And when there is a physical location for a particular resource, we identify that resource using a URL. And then we have IRI, wherein IRI is a URI itself, but it is extended to the universal encoded character set. Okay, and then we have context. There could be different contexts in which the knowledge is true. We can consider this example, wherein Santiago has flight Arica, and it is valid from 1956. So there are different ways of representing this knowledge, right? One way is called as RDF reification, wherein we represent the statement Santiago flight Arica in a statement called E, and we represent another statement wherein it is a statement about E. E itself is a statement, and there is a statement about E. It is a meta statement. E is valid from 1956. Like that, we could have n-ary relationships. There could be multiple relationships, relationship of a relationship. And there could be singleton properties also representing this fact that Santiago is a flight to Arica, which is valid from 1956. So context basically gives the scope of truth, right? When is a set of statements true? So that context becomes necessary when we are designing a knowledge graph. So all these three are important constituents when somebody is looking at designing a knowledge graph. And now let me move on to the different applications where knowledge graph can be used. So there are different domain-specific knowledge graphs. There could be medical knowledge graphs, financial, news, education. If you take, for example, Capital One or Bloomberg or Wells Fargo, all these financial companies have their own domain-specific knowledge graph. And knowledge graphs can be used for question answering, right? You can, the different techniques which go into this are semantic parsing based, information retrieval based, embedding based, deep learning based to answer a particular question. And there can be recommender systems which use knowledge graphs. So knowledge graph becomes some kind of a source of truth, and using that we can recommend different products or services, right? And Amazon itself has a recommendation, right? Whenever you buy a product, it recommends several other products based on your interest. So how does this gather that knowledge? So there is a knowledge graph behind it, which it uses in order to recommend. And we can also do a good information retrieval. That is, we can have document summarization, document representation, ranking of the documents, query representation. All of these can be done using knowledge graphs. And I think most of us now, wherever we try to go and browse something new, we have found social bots, right? These social bots are having some kind of structured knowledge graph behind them to help us answer the questions, whatever we are asking. Or rather, it comes and tries to ask, what do we want? Or what kind of a service is required from that website? So all these social bots use a lot of AI, and knowledge graph is a source of truth, which is the basis for answering questions. And classification is one more big example where knowledge graph is used. And now coming to the research directions. So AI is the buzzword, and knowledge graphs have made it a possibility, right? And these are the different areas where the future research can take its direction. So we can have temporal knowledge graphs, that is time based. See, some set of facts might not be true today, but it was true yesterday, right? When we say the time based representation of knowledge, that is what we call as a temporal knowledge graphs. And knowledge acquisition and completion. So when we curate different knowledge bases, how do we get knowledge, or how do we frame this knowledge base? So the different methods used here are called as knowledge acquisition methods. And how do we complete? So whenever we kind of pick up knowledge from different unstructured knowledge sources, right? It could not be, it is very well kind of to be believed that it might not be complete. So how do we complete such knowledge graphs? There are different techniques for knowledge graph completion. And temporal inferencing for KG completion. So we could have a set of facts, say ABC. AB was true yesterday and C is true only today, but not yesterday. So when we are trying to complete such knowledge graphs, how do we infer based on the time? So that is temporal inferencing for KG completion. And there could be some concepts which keep changing. Say, for example, Pluto was considered a planet long ago, but today it is no longer a planet. So this concept itself has changed, right? So how do we handle such changes in the concept when we try to model the concept? So this is one more direction where we can undertake research, right? And context-based KG evolution. So there could be different contexts wherein a certain set of statements are true. And when we take these multiple contexts, how does the knowledge graph keep changing? And knowledge graph semantic embeddings, right? If we want to infer more knowledge, how do we use embeddings in the knowledge graph? And knowledge graph consistency and verification. So say when we integrate multiple knowledge graphs, so we have to see that the actual knowledge inferred out of it is consistent. It is logically consistent, right? And maintaining that logical consistency in the knowledge graph is another key challenge. And nowadays it is becoming more popular to have personalized knowledge graphs. When you consider Alexa, right? Alexa, every day it kinds of tries to learn from how we communicate to Alexa, right? And so it kind of has its own personalized knowledge graph for the user or the owner of Alexa. So personalized knowledge graphs are another area, and privacy and security is a main concern because our data is available everywhere, and there are machine learning algorithms, artificial intelligence algorithms running on this data. So privacy and security becomes an important concern. And we have multilingual knowledge graphs, right? Knowledge graphs can have multiple languages. Then how do we handle them? So all of these are, one second, the minute I mentioned Alexa, my Alexa turned on, just a second. Yeah. So we can have multilingual knowledge graph. So these are some of the different areas where research can take direction, and we could have additional knowledge from knowledge graphs. And here I come to an end of my monologue. So I would appreciate if there are any questions at this point of time.
Hello. Sir, ನನಗೆ ಒಂದು question ಇತ್ತು.
Madam.
Sir, we are not able to hear you.
One second.
Yeah. Madam, Malini madam, please ask.
Sorry, I am on mute. Yeah, hope I am audible now.
Yeah,
ma'am, I have a simple question actually. You have explained knowledge graph related contents very nicely, especially the research directions in this particular field. I have a basic question related to how do you compare between a mind map and a knowledge graph?
Okay.
Whether mind map fits in knowledge graph or whether knowledge graph needs mind mapping.
Okay. A very good question, ma'am. So thank you for that. Let me attempt this way. So we have, when we think of a topic, there is a map, right? When we connect all the related concepts, right?
Yes.
And so this is basically a graph, but not exactly a knowledge graph, because the ontology or the semantic basis of the facts might not be complete in this, right? So say maybe a mind map of engineering subjects, right? So whatever comes to the mind at that point of time, right? All of them are connected in one way, right? But there could be, I would say that it is not a complete knowledge graph, and there could be many other ontologies which can add to this to make it a complete knowledge graph, right? Does that answer my question?
Okay, ma'am. Around 80% I'm clear.
Okay. So basically, like, one more thing is identity. So if you see the constituents which become important in designing a knowledge graph, we have identity, right?
Yes,
so
yes.
in the mind map, identity is not there, right? The mapping to exact real world entity is not there. That uniqueness of the concept is not there, right?
Yeah. Entity part is clear, correct.
And schemas, okay, fairly there. We have the connection, and the context is also very much there. Yeah, I think identity is one thing which we need to add, and mapping to the external sources and providing more semantic basis to the mind map makes it a knowledge graph, in my opinion.
Yeah. Semantically they are correct. Syntactically they are different.
Yeah, makes sense.
Thank you.
Madam, one question here, and regarding that machine learning, artificial intelligence, and knowledge management. So, what is the link between all these three? Please throw some light on this.
Okay. So, artificial intelligence has been there from quite a long time, right? And it is materializing these days. There was a time wherein many people started talking that AI is not going to work. It is not something which will happen ever. But AI, right now we have a lot of algorithms wherein we are trying to represent human knowledge in systems, in machines. So how do we make machines learn and think like humans? Machine learning is this part wherein we kind of program ways wherein machine can think like humans. So machine learning is that part of it. And artificial intelligence is at the core of all of these, wherein we are trying to make machines think and work like humans. And what was the other thing that you mentioned? Okay, knowledge graph is the ingredient which helps making AI a possibility. So right now we have a lot of robotic systems, and I think last year, right, somewhere in Shimuga, we I think even in Bangalore it should be there, but there was that robo server that is in restaurants. There was a robotic server trying to serve food to tables. So all of this is becoming a possibility because of knowledge graphs and machine learning all coming together, right? So knowledge graph is something which is like a input for artificial intelligence to become a reality. And machine learning are a set of algorithms which help any dumb machine to become smarter. Does that answer my answer your question?
Yeah. Madam Sana, madam.
Yes. Thank you, ma'am, for your enlightening speech on how to use the knowledge graphs to represent the data on the knowledge and related aspects like semantic graphs and the research direction in the particular domain. So we convey our sincere thanks to your time and effort in delivering this talk. Thank you. Now I request our beloved principal, Dr. Mrutyunjaya Vilatte sir, to address the gathering.
Okay, thank you. Good morning, everyone. I seek the blessings of His Holiness Jagadguru Sri Shivaratri Deshikendra Mahaswamiji, and my pranams to the Sutturu Guru Parampari. Actually, the series of programs have been planned to celebrate the Jayanti of His Holiness Dr. Rajendra Mahaswamiji, 106th Jayanti celebrations. And he was instrumental in founding this JSS Mahavidyapita, and definitely till 1986, the Mahavidyapita has established around 76 institutions, and from that point onwards, the present Pontiff Sri Jagadguru Sri Shivaratri Deshikendra Mahaswamiji has taken it to all the states and even at the international level. And today, JSS Mahavidyapita is recognized for its services in all the fields with more than 324 institutions. Actually, his birthday celebrations are on August 29th, and for a complete 1 month of this duration, all the institutions celebrate. And we have planned, actually, madam, on 25th of this month, and before that, a series of programs all the departments have planned, and your lecture was the first in the series. And I thank you wholeheartedly for accepting our invitation and giving us a lot of information about the knowledge graph fabric for enterprise data. Basically, what you said, the ontology, in a one single sentence, I would say it is a philosophy. Okay, and philosophy for today's engineers is known through the research. Okay, and research has become an integral part in today's education. And definitely you have discussed a lot of parameters, how the data can be considered for various research processes, and identify that the data it can be used for developing new solutions in all the fields. That is what we all understand. And definitely this topic is of a very good interest and very useful for both all my colleagues as well as students. And for having arranged this particular program, this lecture program, I take this opportunity to congratulate and appreciate the Department of Information Science and Engineering, particularly Dr. Ashok and Dr. Rekha and their complete team. And once again, my thanks to Dr. Pallavi Karanth, and thank you, madam. And definitely, once the things are completely clear, we'll be conducting offline programs, and please do visit our institution. Thank you.
Thank you very much.
Everyone. Thank you, everyone. Yeah.
Thank you for this opportunity. It was
Madam, please.
yeah, it was good to interact with academia.
Madam, control, please.
Thank you.
Mic on ಮಾಡಿ ಸಾನ.
Thank you.
Mic on.
Thank you, sir. At the end of the session, now I would like to thank our Joint Director, Dr. H.R. Mahadeva Swami, sir, who honored this event with this inspirational thoughts. I would like to thank our Prelude Principal, Dr. Mrityunjay V. Latte, sir, for his constant support. I would like to thank Dr. Pallavi Karanth, madam. Our sincere thanks to you, ma'am, for delivering this talk. I would also like to thank our Dean Research and Professor Dr. D.V. Ashoka, sir, for organizing this event and making it happen. I would like to thank our HOD, madam, Dr. Rekha PM, madam, for making this event happen. And our sincere thanks to Dr. Ravindra and team JSS AHER for providing this digital platform for us. And lastly, I would like to thank all the deans, HODs, staff members, and the students who are making this event a grand success. Thank you all.
Thank you, sir. Thank you, madam.
Okay, thank you, madam. Namaste. Thank you. Please do visit.
Thank you.
Sir. Namaste. Thank you. Sir, okay, one minute. Shall we close? Okay.
Yeah.
Ashok.
Okay. Thank you, sir.
Thank you. Thank you, madam.
Thank you, sir.
Thank you, sir.
Thank you, madam.
Thank you.
Professor BPS, thank you for joining.
Thank you, sir. Thank you very much.
Thank you, sir.